To get the maximum value from the many functionalities of the Student VectorCalculus package, the user has to understand its underlying structures and the relationships between them. So, this webinar is designed to answer the question, what does the user need to know about this package to implement it efficiently and effectively? We'll get a first insight when we take some initial steps. So pick as a starting point. Open package, load it, launch it, start poking around. Find this vector command. Apply it to this list UV. You get U plus V, there's an EX, EY. Probably these are I and J. Yeah, okay, makes sense. Suppose you put polar as an option to vector. Then now you get ER and E theta. And the X and the Y seem to be now interpreted as the polar components. Map to basis command is the change of coordinate command. So here's this vector, and we're changing it to polar coordinates. Well, again comes this ER, E theta, and the X and the Y are now interpreted as Cartesian things because the root of x squared plus y squared is r. This is stuff that goes in front of the r vector. And then arctan, the two-component arctangent yx, puts it into all four quadrants. That's the theta thing. Still not clear what's happening. And this is vector field command. Now the vector field command has this x and y, but now the ex and ey have a bar on it. What's the difference between this ex and ey and the ex and ey with a bar on it? What happens if we do a vector field in polar coordinates? Now you have an ER with a bar on it, an E theta with a bar on it. X is interpreted as the thing that goes with the R vector. Y is interpreted as the thing that goes with the theta vector. Vector field swapped over to polar coordinates. Now all you get is ER with a bar on it and an R. Well, think about that for a second. The vector field XY, that's a radial field. You go over to polar coordinates, it's going to be radial. Well, it kind of makes sense. But it also implies that Maple must know something about this X and Y. Suppose you change the X and Y to just a plain U and V. See if Maple knows something about the U and the V. No, you get something different. You don't get what you got here. Maple is now giving you all of this ER bar, all of this E theta bar. Now wait, we know how to transform a vector from Cartesian to, let's say, polar coordinates from first principles. So let's try that. Position vector, x, y, r cos theta, r sine theta. Differentiate position vector with respect to r. You get a unit tangent vector on coordinate curve. It's unit. I'll put a little cap or hat on it to indicate its unit. Differentiate with respect to theta, you get the natural tangent vector. It's not a unit vector. These are the vectors that are used in differential geometry. In Maple and in much of the applications, the basis vectors are taken as unit vectors. Just knock off the r here and you'll see you get a unit vector. So you have to keep that distinction in mind. At any rate, these two column vectors, this one and this one, are Cartesian because they refer to an ij basis. So you can formally solve these two equations for I and j in terms of ER and E theta. That's the expressions you get here. Then you take a Cartesian vector, the I and the j. Replace the I and the j with these two expressions. cos minus sine, that one goes here. Sine plus cos, that one goes here. There's an ER and an ER, so you collect with respect to ER. You get U cos V sine, and you collect with respect to E theta. You get minus U sine, that's this term, and V cosine, that's this term. And if you compare to what Maple produced, it's the same. So Maple has produced the correct expression. These E bar basis vectors must be our unit moving basis vectors that we computed here by hand from first principles. That leaves us with the question, or two questions really. What are these unbarred basis vectors? What do they mean in distinction to these barred basis vectors? The other thing is, why here, when we used x and y, we got this output, but when we used u and v, we got this output. So probably Maple knows something about x and y that it doesn't know about u and v, because clearly this is a radial field and this is a radial field of polar coordinates. If Maple doesn't know something about u and v that it does know about x and y, then it does not make that simplification. So we have to explore that. The mystery of the distinction between these barred and unbarred basis vectors stems from this feature of the vector calculus packages. The identification of point and position vector. Okay, in Cartesian coordinates, point AB is identified with the position vector AI plus BJ. What this package does is it carries that identification over to non-Cartesian coordinates. So a point is identified with a position vector somehow. All right. In order to do that, this package creates a fictitious position vector in non-Cartesian coordinates. Now recall that at top level, points in Maple are lists generally, square brackets, lists. And they don't carry a coordinate system. They're just two numbers. In the vector calculus packages, points are represented as a vector so that they can carry a coordinate system. So how does this package identify a point or represent a point as some kind of a vector in a non-Cartesian coordinate system? So let's answer these questions by looking at this example. We'll illustrate in polar coordinates what Maple is actually doing. Cartesian plane, xy. On the Cartesian plane, we have superimposed the polar coordinate curves, concentric circles, radial lines. We have drawn in the unit moving tangent vectors, ER and E theta. Again, I put a cap on it to indicate their unit. Now, if you know an x and y pair, you can use these formulas to calculate the r theta equivalent. That r theta equivalent represents a point in a rectangular form of the polar plane, r-axis, theta axis. In this plane, the vectors, these invented vectors, E, R, and E theta with no hat or no bar on it, they're unit vectors, they behave like I and J in the Cartesian plane. And in terms of ER and E theta, the polar point with coordinates r theta is represented as a position vector in terms of these two unbarred basis vectors, er and e theta. Now, clearly, the reverse mapping, if you know an r and a theta pair, you use these formulas to compute the equivalent x and y pair. So what we have taken as the xy pair for the point xy is rendered as the vector. This is r, x squared plus y squared square root, er, so much of this unit vector, and then the arctangent, either y over x, or you get a four quadrant placement if you say y comma x, the two argument arctangent, e theta, which is this vector. Okay, so e, r, and e theta, those vectors without a bar, are these pseudo fictitious vectors that represent points. So what Maple uses as e bar, the typical textbook would probably write as an e hat. These are the moving basis vectors in the polar representation in Cartesian coordinates over on the Cartesian plane. And there's one other thing to note about these e bar basis vectors, moving basis vectors. They're position dependent, but in Maple, they are just symbols. They do not carry the pointwise information that you would expect them to. And I've always believed that the source of the problem is there was no way to attach coordinates to the point. That pseudo vector, fictitious vector thing did not allow these symbols to carry a point information. So all of the commands that manipulate objects, vector objects in Maple, have been taught to figure out the point dependence of these basis vectors when doing calculations with those objects. We'll see that further. Let's look at coordinates next. Okay, the student package knows these 5 coordinate systems: Cartesian, 2 and 3 variables, polar, cylindrical, spherical. It also knows default coordinate names for the coordinate variables: xy, xyz, r theta, z, r phi theta. Now that explains why way back here Maple knew something about x and y, but didn't know something about u and v. In the vector calculus package itself, the big package, all of the known systems in Maple, the orthonormal systems that Maple can work with, they're known, but there are no default coordinate variable names. So you constantly have to tell Maple the name of the system you're in and the variables you're using. But here, if you are just using these common systems, you can get a lot of mileage out of just using the default coordinate variable names, and you don't have to keep inserting instructions to Maple about what names you are using and what system you're in. Now, I mentioned this default variable coordinate names, but I want to talk about spherical coordinates. The convention here in Maple is that no matter what name you give these two angles, doesn't matter. You can call them theta phi, phi theta, UV, PQ, RS. Well, you wouldn't use R. Whatever. It doesn't matter. It's the position in this triple that matters. This middle variable is the angle down from the z-axis. And this third variable is the angle around the z-axis. And that's kind of the math convention. The physics engineering convention is to do just the opposite. It's to call the angle down from the z-axis theta, and the one around the z-axis phi. And this can lead to a great deal of confusion unless you understand that the convention here is if you put theta here, then theta will be the angle down. And if you put phi here, phi will be the angle around. So you have to understand what is the convention that you're using and how to make Maple conform to that convention. Okay, there is an ambient coordinate system when the package is loaded. That's Cartesian. In vector calculus package, you often have to change the ambient coordinates, redefine what it is, and therefore you have to define what the coordinate variables are. So there's a lot of changing of coordinate systems. You do not have to do very much of that in the student package, and that's why I say the student package is a very forgiving nature. Now, the commands for manipulating the coordinate system would be these two. The get coordinate command will get you the ambient coordinate system or will get you the coordinate system on a specific object. The set coordinate command will set the ambient coordinates. If you just say polar, it would set polar with the default coordinate variable names. If you want to use a different set of coordinate variable names, you add it in this list, which is appended to the word polar. Hey, look, if you're doing theta and you have to type out theta multiple times, you might say, wait a minute, let's just call that angle t. Well, how do you tell Maple? How do you override Maple's use of theta? You want to use t. So you do it this way. And the same thing for circle. This is, you have to type out phi, theta, or you have to use 2D math typeset input so that you were just inputting this symbol, phi and theta. What are the vector objects that this package recognizes? So let's begin with a table of these objects. Okay, there are 4. Free vector, rooted vector, position vector, vector field. Free vector is essentially a point. These will display with the unbarred basis vectors. And you can enter it with these wedge brackets, which are just inequality symbols. Or you could use the matrix palette. You could enter a vector with the matrix palette. You can use the vector command. And whether you give a list of components or you have the angle brackets, it's the same thing. Now, the reason for using the vector command is that's the only way you're going to attach a coordinate system. Different from the ambient coordinate system. See, if you do this, it's going to pick up the ambient coordinates. If you want to change, then you would use the vector command, and you don't have to change the ambient system. You leave the ambient system alone. You just add polar, and then these are interpreted as the polar components. And if you want to change the name of the variables, you just use polar. It will list of the new names. So that's a free vector. It's a point. Rooted vector. You know that you can take a vector in a Cartesian plane and you can translate it parallel to itself so that its tail is now sitting at some place other than the origin. The rooted vector is a vector that remembers its root point, or where its tail belongs. And you'll notice the root is given as a list, and then the vector is a vector. You can name it or give it as a vector. Position vector. Okay, so this is the true Cartesian position vector that starts at the origin and goes out to a point. But if the components depend on a parameter, then this position vector defines a curve. And it can be defined in different coordinate system, but it will always be represented as a Cartesian vector. And here I've just done it for spherical. So this spherical one has a 2-parameter dependence, so the position vector is actually defining a surface. So the position vector command defines a point, a curve, or a surface. There's a companion position to the position vector command. It's called plot position vector, and you'll see that when I talk about visualization. This plot position vector command, in conjunction with the position vector definition, allows you to draw various vectors along either the curve or surface. You can put tangent vectors, normal vectors, binormal vectors, derivatives, first, second, third derivative. So you can get acceleration vectors drawn along a curve, drawn on the surface. You name it. You define an arbitrary vector field and have its arrows emanate from the curve or surface. So position vector and its companion position, plot position vector, very, very useful commands. Vector field. This is what you expect. Vector field creates arrows at every point. The syntax would be something like, here's angle brackets, F, G are components, variables. You can do it in polar coordinates. These are the things that have barred basis vectors. These are the things that have unbarred basis vectors. A vector here defined with a variable. So suppose this was t squared. That would not be a vector field. Okay, so there's this special vector field command that creates the object called vector field. Now, when you see down here in visualization, we'll also find that the vector field command takes as an option the ability to draw the arrows of the field. It's a plot option, which we'll see. To make sure that I've given the appropriate detail for each of these 4 types of vector objects, I made some additional tables, use some examples of what things look like. Free vector, using angle brackets, this is what the return would be. You have those unbarred basis vectors, 2, 3 dimensions. If you use vector with polar, then this is a point in polar coordinates. Cylindrical is a point in cylindrical coordinates. Spherical is a point in spherical coordinates. And again, for historic reasons, free vector with a parameter is used to represent a curve because the initial version of this package did not have either rooted vector or position vector. So these two objects didn't exist in the original package. It was either a free vector, which is a point, or a vector field. No provision was made for a curve. So the curve was represented as a free vector. When position vector and plot position vector commands were added, the historic use of the free vector did not get removed. So it's still there. So commands that require a curve use the free vector. But you could use the position vector, but you can also use the original construction of the free vector. To illustrate the rooted vector, I'm just going to draw you this graph. Rooted vector command, root vector, root point, list 1, 2. The vector has components minus 2, 1. So this is the point 1, 2, the root point, and the components of the vector minus 2, 1. Just to make the thing look accurate. Okay, rooted vector, and I draw this arrow with the plot vector command. And we'll talk about the plot vector command more down here in visualization, but the plot vector command is in this package. It's useful beyond belief. There's an arrow command in two places in Maple. The original arrow command was in plot tools, then they added an arrow command to the plots package. They have different syntax. And the syntax is enormously complicated. This plot vector command will take rooted vectors, position vectors, and free vectors, put them in a list, plot vector, you get a graph of the arrows. It is so much more convenient when you're trying to figure out what do these vectors look like, to use this plot vector command than to convert each vector to an arrow and then use the other package approach to drawing arrows. Plot vector. We'll talk about it more when we hit visualization. Some illustrations and remarks about the position vector command. Position vector takes a list. If you have a coordinate system name here, then these two variables, these two expressions, are taken to be the polar components. But the representation of the position vector is always Cartesian, so this is taken as r. So here you have your s squared is taken as r cos theta, because this cubed is taken as theta in three variables: x, y, f of x and y, x, y, f of x and y. This would describe a surface. This is a one-parameter representation. It would describe a curve. If you go to spherical and you let the radius be 1, then you are going to get x equals r sine phi cos theta, y is sine phi sine theta, z is cos r cos phi, but r is 1, just by saying spherical. So this would be the unit sphere. So we have mentioned the utility of the plot position vector command, because with it you can add vector fields to these curves and surfaces, and we'll do more of that when we get down to visualizations. And finally, a look at some specifics on vector fields. Okay, vector field command applied to a vector creates an object that has these barred basis vectors. So these are the moving basis vectors defined at a point. Components here are UVW, you get UVW, you get these basis vectors. Now do it in pole coordinates. These expressions are interpreted as the R and theta components. ER bar, E theta bar, those would be the vectors with the little unit vectors with the little carets on top that we drew earlier. Moving basis vectors. Here I did it in cylindrical, here I did it in spherical. Some things to note. When you evaluate a vector field at a point, you get a vector, single vector. It is now a rooted vector. It remembers the point at which it was evaluated. In the original version of the package, there was no rooted vector. So when you evaluated a vector field, the vector was rooted at the origin. This is not what you want, right? So we made sure that we got a rooted vector command in here to take care of this. But to evaluate a vector field at a point, you must use this eval vf vector field command. If you simply use eval, the top level eval, what happens is the component gets evaluated at the point, but not the basis vector. That brings up another point. These symbols, E bar R, E bar X, they're just symbols. They don't contain the point information. They don't know where they are. Every command that manipulates a vector field has been coded to take care of the vector location, the basis vector location. So that information is not in the symbol. It's in the command that manipulates the vector field. So if you copy and paste one of these symbols, you just get some nonsense. It's a location in memory of where that object is. But that object itself doesn't contain the point-wise information. The commands that manipulate these vector fields, that's where that information is brought into the picture. The vector field command takes the output equals plot option, right? You put output equals plot, and you get a picture. You get a picture of the arrows. So you do not have to use the field plot command from top level or the plots package. You can do it right from inside this package. And again, we said this before, the free vector with parameters is not a vector field, right? Just because you got parameters x and y doesn't change what's essentially a free vector to a vector field. So this vector field is a special object with its own set of unique properties. Now, what commands are applicable to these basic vector objects? Here are the commands. Basis format. This controls the display of free vectors and vector fields. The default is to display these objects as a sum over basis vectors. And so this is where you see displayed barred basis vectors and unbarred basis vectors. The change makes these objects display as column vectors. That's my preference because of the difficulty of enlightening users to the meaning of the barred and unbarred basis vectors. It's just one extra hurdle that you can skip if you use as your display column vectors. There is an about command It's in this package, this is special. It's uppercase. There's a lowercase about at top level. In this package, it will return information about what kind of basic vector object you're looking at, what are its coordinates, what are its components. We've mentioned the eval vf command. It's used to evaluate a vector field at a point so that you get the correct evaluation of the basis vectors and you end up with a rooted vector. The map to basis command is the change of basis for a vector object. It will work on a free vector, so that's a point, and it works on a vector field. Notice that it does not apply to scalar fields. And the reason why it doesn't apply to scalar fields is there's no scalar field object. Unfortunately, there is no scalar field object, so scalar fields do not carry a coordinate system. They just live in the ambient coordinate system. So if you want to change the field, scalar field, you got to start thinking about changing the ambient coordinate system. But there's a way around that. There is a convert vector command, which will convert between free, rooted, and position vectors. So if you want to swap a free vector to a rooted vector, etc., you use the convert vector command. So we've just seen these 5 commands that apply to vector objects, but in particular, differentiation and integration. So let's look at differentiation. What are the basic differentiation commands? Diff. Now, at top level, diff now automatically maps onto the components of vectors. It didn't do that originally. Originally, they modified diff in the vector calculus packages to automatically differentiate the components of a vector. Then it got moved, that property got moved into the student multivariate calculus, and finally it got moved to top level. So that feature is now a top level feature. However, limit and int in this package map automatically onto the components of vectors. Not true at top level, just in this package. Okay, you can clearly apply a gradient operation to a scalar. That's a differentiation. You compute the divergence of a vector field. Okay, you can't compute the divergence of a free vector. It has to be a vector field. You compute the curl of a vector field, not of a free vector. You compute the curl of a vector field. You can compute the Laplacian of a scalar. You can obtain directional derivative, right? That's this guy, directional derivative of a scalar. Well, this is a multivariate calculus item. There's a command in multivariate calculus, I think it's called directional derivative there. But in the vector calculus package, directional diff will also compute the directional derivative of a vector field. So you have a derivative of a vector field in a specific direction. Okay, and this is a very useful thing because there are some identities in vector calculus that are essentially a directional derivative of a vector. There is a tangent line command that you get back a representation of the tangent line tangent to a curve. And there's a tangent plane command that you get back representation tangent plane tangent to a surface. It is unfortunate that these 2 commands are in the vector calculus package and they're not in the calculus packages. I mean, the tangent line command should be in the calculus 1 package. I mean, besides being here, And the tangent plane command should be in the multivariate calculus package, but it's not. So it's there. Those two commands are extremely useful. Uh, they're in this package, but they really need to be in some of the other packages too. The Frenet-Serre formalism for the analysis of a curve requires a lot of differentiation. So the commands associated with that formalism are these: curvature, radius of curvature, torsion, tangent vector, principal normal, binormal, and a complete TNB frame. Some specifics. Curvature of the curve R, and we have pointed out that initially no provision was made for a curve object, so a free vector was used, and you can continue to use a free vector to represent a curve, and that's the easiest way to represent the curve, and that's what you would apply the curvature command to, and you would apply all of these commands to a curve defined via the free vector. Radius of curvature, you get just the reciprocal. There's an output equals plot option. You get a graph of the curve and the circle of curvature. You don't have to be messing with separate circles and objects and figuring out the radius. You just can see the circle of curvature. Torsion, you get the torsion. Tangent vector, you get a tangent vector. Now initially, there was no way of getting a unit tangent vector, but the command finally got modified to take the option normalized. So you get a unit tangent vector. These three commands, right? These three commands, tangent, principal, normal, binormal, they take output equals plot, so you get a graph of the curve and a representative unit tangent vector. If you say animation, you get a graph of the curve and a representative tangent vector traversing the curve. So principal normal, you get the same features. Output equals plot, output equals animation. Takes the option normalized. Binormal takes the option normalized, output equals plot, output equals animation. TNB frame, from the very beginning, return a sequence of three vectors, T, N, and B, and they will return as unit vectors. And this command also takes output equals plot, you get a graph with the triple, and output equals animation, you get an animation of a triple traversing the curve. Now, to visualize that, I'm going to launch the space curve tutor. All right. Tools, tutors, vector calculus. You see this space curves tutor? Okay, I'm going to launch it from this button. This is the space curves tutor. It has a default curve. You notice that the curve is given as a free vector with a default range. There is a default 5 TNB frames, and you can see how cluttered this looks. The very first thing that I always tell people to do when I'm illustrating this is use constraint scaling and change to a frame. That removes a lot of this clutter from the image. Then, if you really want to see how this thing works, change the number of frames to something like 30 and animate it. So instead, you get one TNB frame traversing the curve. Okay, and this can be rotated. You can look at it from different positions. Okay, and you'll notice that the TNB frame command is being used to get this image, and that's what the command itself would do if you said output equals animation. Okay. Now let's take a look at what this package does with integration of vector objects. The int command. Well, int is a top-level command, but in this package it's modified. It recognizes some predefined domains: circle, ellipse, parallelepiped, rectangle, arbitrary region, sector, sphere, tetrahedron, triangle. The region, the arbitrary region, is defined parametrically. There's one other thing about the int command, and that is at top level, lowercase letter here activates immediately. It computes the integral. If you put an uppercase I, an int, you get the unevaluated integral. You get the inert form. Well, that doesn't work that way here. You have to give this int command the option output equals integral. And that's true for all of these integration commands. 1, 2, 3, 4, 5 of them here. In order to get a display of the unevaluated integral, you have to include the option output equals integral. PathInt command is the line integral of a scalar, right? The line integral along a curve of a scalar ds. It knows some predefined paths of integration: arc, circle, ellipse. This arc applies to circle or ellipse the way sector applies to circle or ellipse. A line or a line segment, and in the plural it means a polygonal line defined by its nodes, and an arbitrary path defined parametrically. And it can be accessed through the context panel. There's a context panel way of setting up a path integral. The line integral is line integral, and it's the first one that was put into the package. It's the line integral of the normal of the tangential component of a vector field. The normal component was not treated, so a flux option had to be added, and we'll talk about that here down here in flux. So when you line integral can be either tangential or normal component, but in this package, line integral means the tangential component. It knows some predetermined paths: arc, circle, circle 3D. So your circle could be in space, ellipse, and the arc applies to circle and ellipse, line segments, and path. You can get a graph, output equals plot, of the vector field, so you get arrows of the vector field, and the integration path if you pick one of these 4 predefined paths. And this also can be accessed through the context panel. There's a surface integral command that will do the surface integral of a scalar. Okay, so f d sigma, where d sigma is the element of surface area, and this command figures out what that element has to be. It knows how to do this surface integral over a box, a sphere, or a surface defined parametrically. And an amazing strength of this command is that this arbitrary surface, parabolic thing or whatever, can be defined over known planar regions. So if you just want that portion of the surface that lives over a circle, or lives over an ellipse, or over a rectangle, or over a region that you can define parametrically, or over a sector of a circle or ellipse, or over a triangle. You can tell this command that that is the portion of the surface that is to be used in the surface integration. And here's where the normal component of the vector field is integrated. That's flux, whereas the line integral is either work or circulation. But flux has its own command, integral of the normal component. Now, it could be over the flux through a line, right? This could be planar, flux through a line. And so there's predefined curves, arc, which applies to circle or ellipse, line, line segment, polygonal line, and a path, arbitrary path defined parametrically. You can get a graph if you pick one of these four predefined curves. And the graph shows the field and the normal vectors along, some normal vectors along the curve. So if it's 3 dimensions, if it's a surface, then it's a double integral over the surface, f dot n, d sigma. The command figures out d sigma. Okay. It recognizes box, sphere, and surface. And those surfaces can be defined over these planar regions. If you use one of box, sphere, or surface, not using any of these planar regions, then you can get a graph that shows the arrows of the vector field and the surface over which you're integrating. And you get some normal vectors drawn in that. Flux through curves and surfaces can be obtained through a set of task templates. Okay, tools, tasks, browse, table of contents, vector calculus, integration, flux, 2D or 3D. Okay, so through a surface defined over a disk. All right, you buttons and boxes, you fill in the fields. You don't have to know the syntax of the flux command, how to make it integrate over this piece of the surface or over that piece of the surface. Scalar and vector potential. Vector field, scalar potential, vector field, vector potential. So those are integrations essentially, and those commands will return the appropriate potentials. I think it's time to stop here. There's a whole lot more to tell you, and I think we're going to put that off to a second session, next webinar, next month, where we'll continue from where we stopped here. If you want these or this file, this worksheet, you can send me an email. You can send it to rlopez@maplesoft.com. I'm going to type that here, rlopez@maplesoft.com, and you can ask for the worksheet. However, I'm going to hold your request until after I finish the second part of this presentation, of this webinar, and I will send you the whole worksheet at that time. I'm not going to send you this whole worksheet having only covered half of it. So you can send me an email, ask for the worksheet. I will save that email until next month when I finish the presentation, and then I will send out the copy of the worksheet to who's ever asked for it. And right now we can see if there are any questions.